Alright, this is Jack Jackson back with our next of these series of lectures on transformations. This one is on reflections. And in general, if a reflection is just a mirror image over a line, general reflections are a little bit harder to do in full generality, but there are three specific ones that are fairly easy to see, and they correspond to very simple changes in the formula. So we're going to look just at these three types of reflections. The first one we're going to look at is a reflection about the y-axis. And to do that, all we have to do is replace x by the opposite of x in the formula. And that will end up reflecting the graph over the y-axis. Okay? If this turns out to be the same, then of course we say it's symmetric with respect to this transformation. This is a reflective symmetry, and probably the most common way you think of something being symmetric is a reflective symmetry. So usually if somebody just says it's symmetric, they mean a reflective symmetry, and in this case it's a reflection over the y-axis. So if you can change x to minus x and the formula turns out to be the same, it has y-axis symmetry. Let's start by looking at this one over here with y equals x cubed. So here it is in purple as y equals x cubed. We are changing the sign on x. Notice it's underneath the cube, so it's changing x to minus x, leaving y alone, the way we're thinking of it now. So notice again we leave y alone, so those are the same. And notice when we take a point from its preimage to its image, we change the sign on the x. Now where's that point going to go? Well, let's think about it. This point over here in the preimage is in the fourth quadrant, and this one, its image is going to go over to the, this is in the, fourth quadrant. No, third quadrant, negative, third quadrant, and its image is in the fourth quadrant. First quadrant points like 2, 8 are going to be sent to second quadrant points like negative 2, 8. And so it's going to flip over the y-axis. So the stuff in the first quadrant is going to go to the second, and the stuff in the third is going to go over to the fourth. Okay, and since that ends up being a different set of points, it's not symmetric with respect to the y-axis. But when we look at our good old friend here, y equals x squared, this time when we change the sign on the y, notice points are moved. In fact, the only point that's fixed in any of these are points that are on the y-axis. Because when we, on the y-axis. So if we change the sign on x and it stays the same, that means x has to be 0. Well, if x is 0, you're on the y-axis. So it's going to, and of course that makes sense because when you reflect something, anything on the mirror line is going to be fixed. But all the other points move. For example, negative 1, 1 moves to 1, 1. Negative 2, 4 moves to 2, 4. But what also happens, though, is 2, 4 moves to negative 2, 4. So if you look at right here, let's just look at this part of the table right here. It's the same 3 points, just in a different order. And so ultimately when it flips over the y-axis, the first quadrant goes to the second goes back to take its place in the first. Of course, the point at the origin is fixed, and even though individually points move, collectively the points stay the same. So this graph is symmetric with respect to the y-axis. Symmetry, especially reflective and rotational symmetries, are very important for us for some reason. I suspect partially because our bodies have approximate symmetry, not exact symmetry, but kind of a reflective symmetry, approximately. And but whatever reason it is, we have a tendency to like things that are symmetric. And you're going to see a lot of symmetry in nature, and you're going to see a lot of symmetry in design for human designs. Now, of course, if we want to reflect over the y-axis, we change the sign on x. So if we want to reflect over the x-axis, guess what? We're going to change the sign on y. And so we replace y by the opposite of y, then it's going to be reflected about the axis. So here we change the sign on y. Well, notice that this doesn't really violate what we said about the table being opposite from the formula. It's kind of the same, but this is a function whose its own inverse, where you change the sign. So multiplying by negative 1, dividing by negative 1 are the same thing. They each change the sign, and they each undo each other. So changing the sign, the opposite is to change it back. So either way we go, this time we're leaving the x alone, so this stays the same, and we change the signs on y. In this case, on the red one, that gives us actually a different table, and that's going to be a flip over the y-axis. That arrow is actually upside down. Let's try this again. Because all of these are going, the blue is the pre-image, and so we see that is going to be, that point's going to be reflected over the axis from the first quadrant down to the fourth quadrant, and from the second quadrant down to the third. This time points on the x-axis are left alone. Okay, these arrows are correct on this one over here. We start with y equals x cubed. This time the first quadrant's flipped down to the fourth, and the third quadrant's flipped up to the second. And so we flip this over the x-axis this way. I think something's out of whack here on my graph. Let me look at something here real fast. Yeah, this thing, the whole graph has gotten a little bit out of whack here. Let's see what I can do here. There we go. That's what it should look like. And so the original is the purple one, and the green is the other one. So let me go back in here and kind of fix that. This is actually the original, okay, which is the purple one, and the new one is the green one. So this formula is for the purple, and this formula here, where we switch the sign on y, is the green. So I'm trying to color code all these things. There we go, that looks better. Okay. Alright, let's get back down to where we were. Now we have one more, so we've done a flip over the x and the y axis. Now we're going to do one more flip, a reflection. And this one actually gives us something called the inverse relation. There's going to be a whole nother video, or you should have already watched a whole nother video about inverse relations. But here let's review that as well. Or you can watch this one first, then the other one, doesn't really matter. We have y equals x squared. It turns out to get a reflection over the line y equals x, what we have to do is switch x and y. I'll explain that more in the other video. But this gives us what we call the inverse relation. So you just swap the ordered pairs. So instead of, if we have -3, 9 on the original, then 9, -3 is on the inverse. Okay? It's 3, 9, 9, 3. 2, 8, 8, 2. And so here we can see the inverse relation. And for reference, I gave the mirror line of y equals x. And you can see a reflection over that line. And you can tell it's a reflection because if you come in perpendicular to that, so you start the pre-image up here, some point AB, and you follow that perpendicular distance straight to the reflection line, y equals x, and then keep going the same distance the other side, you'll be at your image, BA. And so you get a reflection over that line. Okay? And so here we get y equals x cubed and x equals y cubed, or y equals cube root of x. Those are opposite functions of each other, inverse functions. So, in general, a reflection requires that we specify a mirror line, call it L, and when we move the pre-image points to the same distance on the other side of the mirror line, so that the line containing the pre-image and image, I should say the line segment going from the pre-image to the image point is perpendicularly bisected by the mirror line. That's geometrically what it means to be a reflection, and that's exactly what's happening here. Now, general reflections, as I mentioned earlier, are going to require more work than we're going to do in this semester's course, so we're only going to consider these three specific ones. Reflect about the x-axis, change y to minus y. Reflect about the y-axis, change x to minus x. Reflect over the line y equals x, switch x and y. This does give you a congruent image on a reflection. It is oriented differently because it's been reflected, but all distances and angles are preserved in the original, and if you flip it over, you can move it around. You're going to be able to land one pre-image right on the same as the image, the same size and shape. So you do get a congruent image. Fixed points are points on the mirror line in any reflection. And a figure that has line symmetry is its own mirror image over that line. And so we will look at many graphs that have symmetry with respect to one of the three reflections we're studying. And of course, any symmetry is a special property, so most relations don't have any symmetries at all, much less any of these particular ones. Okay? But some graphs do, and that's a special case. So we'll talk next little video about rotations. Actually, before we go on to that, I'm sorry, let's look at some examples here. So if I take y equals absolute value of x plus 6, okay, that's going to be a right angle, but notice it's been shifted to the left 6 from the origin, and so we have a nice right angle. If I replace x by minus x, it's going to be reflected over the y-axis. If instead I replace y by minus y, it's going to be flipped over the x-axis and be flipped upside down. So you can kind of see those examples. Let's see, how about y equals x to the 5 force power. That's only in the first quadrant. How do we get a mirror image down in the fourth quadrant? Okay, we're going to flip over the x-axis. We need positive y's to become negative y's. So we put a negative y in place of y, and that'll flip it over. How do we get it in the first quadrant? Take the original and replace x by, need parentheses around it, replace x by negative x. That'll flip it over to that quadrant. How can we get it in the third quadrant? Well, you need both flips. And that, in fact, turns out to be the same thing as rotating 180 degrees. We're going to go ahead and do rotations now. So rotations turned out to be, in general, if you have two lines that intersect, you can get an image. If you do a flip over one line and then a flip over the other line, two reflections in sequence, and compose those two reflections, then what you're going to end up with, you could get there from the original pre-image to the final image in one step by a single rotation, and it's about the center of that. The center of the rotation is where the two lines meet, and the angle is twice the angle between the lines. So in our case, the two lines that we're flipping over are the x and y axes, which meet at right angles, and so we're going to be rotating about the origin when we do the two flips, and we're going to rotate 180 degrees. So if I get rid of some of these others, let's see here. Let's just get rid of those. Go back to this one, and again, if I put a negative on y and x, we can think of that as flip, flip, or we can also think of that as rotating around the origin 180 degrees, a half circle. Let's look at something else here. Going back to our example here where we had the function y equals the square root of x, and I can change a and b. If I change a to a negative power, or not a negative, but a negative number, all of a sudden now we've got a flip as well as possibly a stretch. If it's just a negative 1, notice we have flipped exactly over the y-axis. Okay, I put that back to 1, it's back to the original. And now if we change b to -1, that's a flip over the x-axis. And again, it doesn't matter what function I put in here to begin with. I can go in here and change the function. Instead of, x to the 1/2, I can do x to the whatever, 2/3. And now we see it's the black one is the original and the red one has been flipped over the axis. Or I can change it to absolute value of x. Let's see. Like that. It's been flipped over. How about a little stretch in there? Whatever we do, we still get just a flipped over thing here. If I were to switch this, I'm going to get a certain amount of stretch, but I could get a flip and a stretch by the negative. So think of the negative as being the flip, and the other part of the power as being the stretch. So I'm going to go back to my original one I had there. Okay, and again, if I make them both negative, so this is going to say flip here, and if I end up making this one negative, that's going to flip it over again, but over the x-axis once, the y-axis the other time, and now we're going to get the third quadrant where we just essentially get the same thing by just rotating around. And notice again, if you look down here at the points, every one of them has changed the sign of both x and y. So we're not going to do, just as we didn't do reflections in general, we're not going to do rotations in general, but we are going to do that one specific rotation. Now, some graphs, if you take one like y equals x cubed, okay, and let's clear this out. And if you change the sign on both y and x, should we put that in parentheses? Notice that it lands back collectively where it ends up, where it started. But notice that the only point that's really not changed at all is the origin when you do a rotation. When you do a rotation, you've got a center of your rotation. The center of ours is at the origin. So the only point that's really fixed is the origin. However, the stuff in the first quadrant gets rotated down to the third quadrant gets rotated up to the first, and ultimately we get the same collective set of points. So this has a rotation symmetry, specifically 180-degree rotation symmetry about the origin. So this has what we call origin symmetry. Okay. Alright, let's take a look at back here. So the rotation. So a general reflection requires we specify a general rotation, that should say, requires that we specify a point that's the center of the rotation and an angle of rotation. We then move the pre-image points along part of a circular path to the image point. So the image and pre-image points are the same distance from the center, and the angle from pre-image to center to image is the angle of rotation. In general, when we perform two reflections about intersecting lines, the net result is a rotation about the intersection of the two lines through an angle twice as big as the angle between the two lines. Therefore, if we reflect over both the x and y axes, the net result is a rotation of 180 degrees about the origin. General reflections and rotations require more work than we're going to do this semester. Even general rotation about the origins require the use of trigonometry, so we will only consider this one easily obtained rotation of 180 degrees about the origin. Other ones will have to wait for at least for a trig class, if not later. The image of any rotation, any figure, you take it and take a pre-image, rotate it and get an image. Your image will be congruent to the original. angles within that will be preserved, as well as distances. So again, the image is the same size and shape. So let's review real fast. Which ones map congruent image, pre-image to congruent image? It was, of course, the identity transformation doesn't do anything, boring. Then there's the translation, reflection, and rotation, or any combination of those, doing one and then the other. That will give you what we call rigid transformations or isometries, things that map congruent images, pre-image to a congruent image. We also had a similarity transformation, and that was where we had a dilation, and so there our figure was scaled back, up or down. It still maintained the same angles, but not the same lengths, but the lengths were proportional. And then when we had a strain, horizontal or vertical strain, actually things got stretched and distorted. The only fixed point of rotation is the center of rotation, and of course you can rotate an image and get the same thing, rotate a pre-image and get the same image. Collectively, that has rotational symmetry. So if we rotate 180 degrees about the origin and get the same thing we start with, it has origin symmetry. So we can test for origin symmetry by replacing x by minus x and y by minus y. If that formula turns out to be the same and graph is the same, then it has origin symmetry. We talked about some power functions that have that. The ones that were in quadrants 1 and 3 had origin symmetry. The ones that were in 1 and 2 had a reflective symmetry about the y-axis. So here we go. If we replace both x by minus x and y by minus y in the formula relation, we obtain a reflection about both axes, which is equivalent to a rotation about the origin through an angle of pi radians, or 180 degrees, or half circle rotation. And we say if the graph turns out to be the same, then it's symmetric with respect to the origin. Y equals x cubed is symmetric with respect to the origin. Y equals x squared is not. And you can see that we've changed both signs here in these tables. And I've tried to indicate what's going on here with the rotation. So the first quadrant gets mapped down to the third, and the second goes around down to the fourth in this example here on the left. Example on the right starts at first and third, rotates. You still got first and third. One lands on top of the other. So in the end, we have collectively the same set of points. So we have origin symmetry. Talk about even and odd in our next video.